Hello everyone, my name is Anthony and I am currently a hardware engineer within the Compute Hardware Design team at Facebook. Within this Rack and Power engineering workshop, I plan to share my observations from a recent survey of 48-volt architectures for an onboard DC-to-DC conversion based on recent industry trends. I hope all of you will find this presentation informative, and please hold your questions until the end to ensure we have sufficient time to walk through all the material. Okay, so before we deep dive into the bulk of this presentation, I think it's worthwhile to give some context and motivation behind 48-volt DC power distribution. So 48-volt has actually been a popular choice for the telecom industry for quite a long time now, and there's actually quite a few good reasons for this. And to name a few, typically when we're using a higher bus voltage, this could reduce the conversion and distribution losses, which yields better end-to-end efficiency. It also enables the use of backup batteries to be used during the power outage conditions or scenarios. And 48 volt is actually still considered a safe voltage level for human contact. Thus, it also reduces some of the risks that could be coming from the maintenance or accidental contact. So there's actually quite a few emerging applications in recent times that is also driving for the higher power density. And to name a few, things such as data analytics, AI, machine learning, computer vision, image processing, biomedical research, and other different types of high performance computing has been a strong motivating factor. So with a lot of emerging applications pushing for a higher power density, numerous challenges actually have begun to surface with the existing 12-volt architecture. So a lot of times, when realizing such designs, careful consideration has to be taken when looking at the trade-offs between efficiency, thermal, and reliability. So, for example, let's take a look at the existing ORV2 rack configuration that typically implements some sort of a shared bus bar design using a 12 volt. So typically, such an approach will possess some sort of a bus bar to motherboard interface, right? Whether this is in the form of a cable or a connector. Popular use case, could be like a Medusa cable, for example, that lets us hot plug the systems into the bus bar relatively easily. Um, and moving to the motherboard side, we would typically find some sort of a hot swap controller or maybe like an eFuse, mainly for the power telemetry and also the fault protection. After that, looking downstream, we would find ourselves with different type of 12 volt converters, and also downstream POLs for the various load devices that need to be supported on your platform. So the first challenge, one must really consider is actually selecting the power shelf to make sure it can actually handle the slew rate and load step requirements of your IT payload. So suppose, this is not a concern, right? The next challenge would be maintaining that 12 volt tolerance band during the large DIDT events. In many scenarios, this can be somewhat bypassed, right, by simply oversizing your current carrying paths, right, such as your connectors and cables. But eventually, you're going to have to deal with the high currents on your motherboard, which a lot of times would require you to use a large amount of PCB space or super SOA MOSFETs just to kind of meet those high current delivery requirements. But even looking forward a little bit more, we start to deal with a lot of copper plane and via current density challenges. Really handling the voltage drop and again maintaining that 12 volt tolerance band continues to be a problem at all stages of this path. So there's a lot of motivation on going towards a 48 volt as definitely a lot of these issues can be mitigated. Okay, so before we look at a few common architectures based on the current 48-volt ecosystem, there's a few important considerations that I want everyone to keep in mind as we work through the material for this presentation. So the architectures presented will be of high-level abstractions, right? So meaning it's not a full representation of the actual implementation. We'll be mainly focusing on the shared bus bar topology, mainly for maybe like an ORV2 or an ORV3 type of application, mainly for simplicity. But actually, a lot of the content here can be directly applied for the AC to DC side as well. If you have a dedicated silver box power supply, for example, And lastly, the observation mentioned are of course based on the typical kind of industry trends over the past few years, and not since the introduction of 48 volt itself. So with that said, there are three common 48 volt architectures that have been proposed, which is namely the two-stage conversion, the hybrid intermediate bus, and also the direct conversion. So as mentioned previously, let's assume a rack power delivery architecture that implements a shared bus bar topology, which is 48 volt in this case. So option one is actually probably the simplest approach of the three, as there's actually minimal change to the existing 12 volt architecture, as what we're doing is actually simply adding an additional conversion stage to step down the 48 volt bus to a 12 volt, which we are used to. So actually, this can be realized either through a introduction of like a separate PDB, mainly like a different power distribution board that you may add to an existing design. Or, if you are working on a new design, you may also consider actually implementing this additional stage directly on the motherboard as well, if space allows for it. Okay, so for option two, instead of having a single regulated second stage bus voltage, it is actually split into a unregulated and a regulated bus. Thus we coined the term hybrid intermediate bus. So the unregulated conversion stage could actually supply loads without strict regulation requirements, right? So for things like XPU or memory or standby rails, the input voltage to the downstream converters may not necessarily need to be 12 volt either. Now, the regulated conversion stage in this case is still required, mainly to support the various 12 volt commodities, such as PCIe cards, storage devices such as SSDs or hard drives, or any other type of add-in cards that you may have on your platform. Okay, so for option three, slightly different than the hybrid intermediate bus approach. Here we actually replace the unregulated conversion stage and directly convert down to POL, right? So this means we'll take 48 volt and convert it down to levels that are acceptable to XPU and memory or different type of standby rails. In most applications, as mentioned in the previous slide, actually the input voltage to such POLs doesn't necessarily have to be 12 volt. But again, the regulated conversion stage is still a necessity here, mainly because we do still need to support the 12 volt commodities that exist on our platform. Okay, so among the various aspects to compare for each option, there are definitely a few that are worthwhile and warrants the further discussion. So the first thing I want to mention is complexity, right? So complexity is mainly looking at the additional design overhead by introducing 48 volt. And another aspect is space utilization, right? So the overall real estate required to implement the architecture. Another aspect to consider is resource intensity, which is mainly referring to the quantity of components needed to actually implement the converter solution. And efficiency, of course, is an aspect of which that we definitely have to take a look at. And this is, of course, looking at the power loss of the solution itself. And finally, another aspect to also talk about is actually scalability, mainly focusing on areas of how flexible is the architecture and what is the overall kind of features or feature support provided. So first, let's take a look at complexity, right? So if we were to rank the three architectures shown, the two-stage would definitely be ranking lower compared to the hybrid intermediate bus, which is the highest, and the direct conversion is somewhere in between. So the main reason why this particular ranking was kind of thought about was because the two-stage approach can primarily be implemented in a very non-intrusive way without much impact to existing 12 volt designs, making the approach relatively simple. The hybrid intermediate bus approach is actually quite complex in general because now you have to deal with a regulated and non-regulated bus for given the exact same design. And the direct approach is probably somewhere in the middle, mainly because now we're introducing 48 volt planes directly into the design, and while still needing the regulated 12 volt as well. So from the space utilization perspective, regardless of whichever architecture that is chosen, additional space is definitely going to be required to accommodate the 48 to 12 volt conversion stage. Because all platforms today typically still require the usage of the various different common commodities. The one thing to mention here is that the hybrid intermediate bus would still require a additional unregulated conversion stage, and direct still needs the regulated 12 volt stage as well. So that's why, in terms of utilization, actually, it's definitely something to consider when looking at the three different architectures. So the next thing is the resource intensity, right? So many converters actually may end up requiring more than itself, and I think this is an aspect I'll talk about a bit more in the future. But definitely, similarly relating back to space utilization, regardless of what is chosen, you pretty much will still require the need of a regulated 12 volt uh, conversion stage. And for the hybrid intermediate bus, we're splitting a single regulated stage into a smaller unregulated and regulated stage. So it may consume slightly more resources compared to the two-stage approach. Um, and finally, for the direct conversion, actually ranks amongst the highest in this case because some topologies may require magnetics and/or large modules to realize. So focusing on the regulation stage itself, direct does not seem to be trending better than traditional synchronous buck in terms of efficiency. Otherwise, probably everyone would be doing this by now. And since two-stage is literally adding an additional conversion stage, the efficiency will definitely take a loss, whereby the hybrid intermediate bus has an opportunity for optimization, depending on what kind of intermediate bus voltage or topology that might be chosen. Scalability is the last thing that I definitely want to highlight, and I think this particular aspect is not so trivial to rank amongst the three, mainly because there's actually a specific area that we need to deep dive further, so I'll leave that for a later slide. So, based on this type of very quick comparison, there's some considerations that, really we have to keep in mind, right? So when we're adopting the 48 volt architecture, this by no means, at this point in time, we can eliminate the 12 volt power rail, right? Mainly because those commodities today still require that regulated 12 volt. And actually, another aspect is we need to actually look into studying the conversion topology trade-offs individually. And, this is actually where things get quite complicated. So the existing 48 volt ecosystem actually is quite diverse today. There are actually various converter topologies and solutions that are readily available. But, there's actually a lot of things that, we have to consider. First of all, does your design require isolation, right, to meet any specific operational and or safety requirements? Another aspect to consider is, as highlighted earlier, does your platform currently utilize any add-in commodities, right? So if so, you probably need to ensure regulated 12 volt bus remains available on your design. And another aspect to also think about is actually, are there any platform form factor or maybe space constraints that need to be considered up front. And this is a separate topic I'll talk about a little bit later. But once you have answers to the majority of these questions, it's really time to look at some of the available converter options. So to translate a specific converter topology into a product today, there are actually three common approaches that are currently used. First would be possibly through a integrated package. Another alternative would be through a brick module, which is a DOSA industry standard. Or we can simply discretely lay out the converter solution onto the PCB. So the integrated package definitely does enable a high power density for applications where space utilization might be the key consideration. But a lot of times, because of the form factor and also the technology involved, it could end up being a proprietary solution. Whereas the brick solution are typically offered by numerous vendors and is a more viable option if space is not exactly the key consideration or challenge. And let's say if neither of those options work for you, then perhaps the most obvious way would be just to discretely lay out the converter solution itself directly onto your motherboard design. So, contrasting to the 12-volt ecosystem, there are definitely some obvious differences here, right? So, in a 12-volt ecosystem, there has always been kind of like this, um, synchronous buck regulator where it's a one-size-fit-all type of solution, right? No matter what you're trying to step down. But actually, in the 48-volt ecosystem, there has been a lot more wide variety of options available, and also as you can see, each option is catered to a specific, use case or form factor. So as mentioned previously, we would revisit the topic scalability separately, mainly because there's actually a few aspects that need to be addressed in greater detail. So first, let's focus on power density and take a look at the trade-offs between choosing a single large or a multiple parallel converter approach. So actually, it turns out the decision is not trivial, and could actually be driven by a variety of reasons. And one thing to consider is actually whether there are any, pre-existing platform constraints. So, for example, let's take a recent feasibility study that was performed on the next generation one-socket Yosemite V3 platform. So what we're looking at here is actually the rear view of the Yosemite V3 chassis. So the conversion stage shall be implemented such that it's most likely going to be where the ambient temperature is going to be the highest. So, using a parallel approach might actually seem like a great idea to reduce the overall power density and help to improve the cooling. Um, but actually, in reality, in order to use a parallel regulation approach, we actually need to handle the current balancing between the modules. And whether we're implementing a passive or a active current sharing approach, sometimes it actually can end up being quite difficult to realize without significantly increasing the space utilization. And the main reason for this is because a lot of times both the input and output needs to be actually designed in such a way that the layout is symmetrical. And another aspect, the parallel current on the output side may not necessarily ever be balanced, right? May have different payloads with different peak excursions that may or may not line up at the same time. So, you know, an alternative, of course, would be to use a, large single stage converter and not have to deal with current sharing concerns at all. But by doing so, we're increasing the power density, which may require a substantial cooling solution to be used, such as the one shown here on the next generation two-socket Sonora Pass platform. So another aspect of scalability that needs to be addressed is actually feature support. And the main reason for this is because not all solutions are made equal. And a lot of times the converter itself may require more resources than just the powertrain. So, for example, if we look back at a two-stage approach, the actual implementation actually, again, as I mentioned, was a high level of abstraction. Right. So in some cases, for example, you might need some sort of a HSC or soft starting circuit for the powertrain itself. And sometimes the converter itself may need a secondary HSC or soft starting stage to ramp up the 12-volt side to, minimize the inrush and those things. Another aspect is, a lot of times we may want to be able to measure a lot of the various telemetries such as like voltage, current, and power, You might be interested in knowing the temperature of the various components in your powertrain. But a lot of times actually, this feature set may not necessarily be consistent between applications. So a lot of times, more circuitry or resources in general have to be used in order to implement the solution. So in terms of summary and next steps, one thing definitely is there are various important considerations when transitioning to a 48 volt architecture. Currently, there's simply no modular approach, right? As I mentioned as well. The use cases and the trade-off study may necessarily be required to actually drive which approach makes sense for you. And also, conversion efficiency is something I didn't touch upon too greatly within this presentation, and that's mainly because this is something that needs to be studied end to end. There's simply no option where you can choose between the three architectures and yield the highest efficiency, right? It really depends on, what kind of payloads your designs require. Does it make sense to use a full regulated solution or non-regulated? Again, there's a lot of those type of platform constraints that actually may end up driving your final decision. So, one thing I think definitely is an area of opportunity where we can all collaborate, and that is within the next generation Open Rack specification that is ongoing. So, namely the ORV3. This is definitely an opportunity to address some of the issues with the existing architecture, um, you know, look at some nice to have features and stuff like that. And definitely to really align on the requirements to develop a common specification, and really guide the industry to collaborate and, develop solutions that are more catered for the ORV3 in general. The main reason why I think this is definitely a good opportunity for us to further explore is mainly because the RV3 currently is trending towards a narrow range 48 volt architecture. So, for those who may have attended the earlier ORV3 introduction presentation, I'm not here to repeat all the material in great detail, but I definitely do want to highlight this particular aspect. So, the general trend for the ORV3 is that we would like to adopt a narrow range 48 volt architecture, right? So, previously in the 48 volt definition, this required the full 40 to 60 volt range to be supported. And this was a primary requirement due to the battery backup units that were used previously. Um, and moving forward, we do see a lot of opportunity where going with a narrow range approach may be a more suitable and efficient way to design the next generation rack. So, some of the key benefits definitely for going with the narrow range 48 volt approach is we can definitely minimize the voltage range significantly. So no longer will we have to use 100 volt devices just because we need to support the 60 volt requirement, right? So both voltage and current ratings can benefit. On the IT gear side, right, there's an opportunity where if we regulate the bus voltage, it might be possible to enable more fixed ratio converters, not necessarily having to have that additional regulated 12 volt stage, which is a huge plus. And in this area, actually, power is flowing more naturally with a lot less software control and dependency. And definitely from the ACDC side, this simplifies the rectifier design with a fixed output voltage as well. Okay, so to end things off, I want to, quickly go through over a call to action, right? So for those of you who may want to kind of keep updated on the various activities that's happening within the Rack and Power subgroup, there's definitely two obvious ways that you can do that. So first, definitely do check out the wiki page that we have, where you can access all of the new and existing specifications that have been contributed. Another aspect is definitely do subscribe to our OCP Rack and Power mailing list. We have a lot of routine meetings and discussions led by various industry working members of the group. And if you have any questions, this is also an excellent way to ask those through this particular mailing list as well. So thank you all for listening to my presentation, and we will now transition to Q&A.
Okay, all right. So I'll be taking any questions here for the next couple of minutes while we're still in the session. So feel free to post in the Q&A tab or directly in the chat. Okay, maybe I'll read out some of the questions from the Q&A for those who may not have seen it. So there was one question about my comment about how the direct conversion has a higher loss. And if so, then why do we even choose that as an option? So it's a good question, actually. And the main reason why I put it as high is I'm mainly looking at it from comparing a 12 volt to POL versus a 48 to POL. So if we look at it from that perspective, in most cases, the efficiency is lower. But actually, if you look at it again, as I mentioned towards the end of the presentation, if you look at it in an end-to-end perspective, there is a possibility that you might end up with a more efficient design, mainly because by doing so, you get rid of the 48 volt to 12 volt conversion stage, which is needed if you wanted to maintain the existing 12 volt architecture. Yeah, so there's a question here from Huawei about hardware experiment results from different topologies. Yeah, so that part I actually didn't include in this part of the presentation, but I'm welcome to take this question. So the main reason why I did not really want to get into that is because it's actually quite difficult to do a fair comparison without actually designing some sort of a test vehicle platform and with specific constraints in mind. So I think as a possible follow-up, we are studying some designs on our Facebook platforms in particular, like the two that we announced through this OCP summit this year, the SNORPASS and the Yosemite V3. We are looking into doing some testing with different type of modules and different type of converter solutions. Hopefully, I can maybe follow up and share some of those results perhaps in the following year, or maybe in the some of our the regional summits, for example. That might be an option. Are there any servers today that use direct 48 volt to 1 volt conversion? Yes, I believe so. Actually, there's quite a few different types of solutions that are available for this. Currently, today, from my side, I don't, but I definitely have seen some solutions and designs that have incorporated that as an option. Okay, let's see. Okay, there's a question about, okay, do you see isolation is still needed in the future, 48 volt and down? So that's a good question. Currently, I think in most of the ORV2 and ORV3 contexts, because the PowerShell provides that isolation, in our case, it probably is not required. But again, your mileage may vary depending on the application. Okay, there's another question. Regarding the narrow DC to DC 50 volt, what is the advantage of having DC to DC on the battery side compared to having a regulated 40 volt to 60 volt DC-DC onboard. Okay, if I understand this question correctly, so the idea here is actually to have the it's actually also good to have the DC-DC on the battery side to be regulated as well, mainly because of peak current sharing related, right? So the idea here is during the high DIDT events, we would be able to possibly use the batteries as kind of like a huge capacitor type of idea. That's kind of the idea why we wanted both things to be regulated, and we wouldn't be using the battery side unless the voltage on the narrow range 50 volt drops below a certain threshold. I believe it's 48 volts today, but that's kind of the considerations that we have right now. Okay, there's a question here. Do I think 5 volt is better intermediate bus voltage than 12? Yeah, so actually in my slide, I hopefully I didn't explicitly say a specific voltage, but definitely that's the optimization point that I mentioned that may end up yielding you better efficiency depending on which intermediate bus voltage you choose. I know sometimes the downstream POL conversions may use a 5 volt or a 3.3 or 7 volt or something like that, right? To reduce the duty ratio and get better efficiency there. So I think that's definitely an optimization opportunity, but there's definitely no kind of like one size fit all approach at this point. Okay. Okay, there's a few questions I'm gonna need to follow up on. I don't exactly have the answers on hand, so I'll try to reply back to those offline later. Okay, yeah. All right, so I think thank you all for attending for this particular session. Feel free to reach out to me offline if you have any further questions. Otherwise, have a good rest of your afternoon.